Most people assume that time is one of the few things the universe can never lose. Stars are born and die. Galaxies collide. Civilizations rise and disappear. Yet through every event, time seems to remain untouched, flowing with quiet indifference in the background. Physics paints a less comfortable picture. There is no universal clock ticking somewhere beyond the cosmos. Einstein showed that time stretches, slows, and bends depending on gravity and motion. A clock orbiting Earth does not keep exactly the same time as one resting on its surface. Two observers moving differently can disagree about how much time has passed, without either being wrong. That discovery changed how we measure time. It did not explain why time has a direction. We remember yesterday, but not tomorrow. Ice melts into water, but puddles never gather themselves back into perfect cubes. Smoke spreads through a room, yet no one has watched it calmly return to the chimney. The equations governing many microscopic interactions remain almost perfectly reversible. If someone played the motion of two atoms colliding backward, the laws of physics would accept it just as readily. The universe appears willing to run in either direction. Our experience does not. That contradiction has occupied physicists for more than a century. The answer most often proposed is not hidden inside clocks or calendars. It lies in probability. Entropy is frequently described as disorder, but that shorthand hides the deeper idea. A more careful description is that entropy measures how many microscopic arrangements can produce the same large-scale state. Some configurations are extraordinarily rare. Others overwhelm almost every possibility. The second law of thermodynamics does not force the universe toward chaos through some invisible command. Instead, higher entropy states are simply vastly more probable than lower entropy ones. Imagine shuffling an enormous deck containing trillions upon trillions of cards. There are countless ways to produce what appears to be a random mixture. There are almost no ways to recreate the exact ordered sequence from which you began. The mathematics quietly favors one outcome over the other. Our everyday world follows those odds. This statistical tendency becomes what physicists call the arrow of time. It is tempting to stop there. If entropy increases, then time moves forward. Mystery solved. Except it is not. That explanation leaves behind an uncomfortable question. Why was entropy low enough in the beginning for any arrow to exist at all? According to our best cosmological models, the early universe shortly after the Big Bang was remarkably smooth. At first glance, that seems like maximum disorder. Yet once gravity enters the picture, an almost perfectly uniform universe represents an extraordinarily low entropy state, one containing enormous untapped potential for stars, galaxies, planets, and eventually life to emerge. That unusually special beginning may be the reason the arrow of time exists today, but why the universe began in such an improbable condition remains an open problem rather than a settled answer. So Wikipedia. In other words, every memory you possess may depend on an initial condition that modern physics still cannot explain, that shifts the investigation. Instead of asking why clocks move forward, we begin asking why the universe ever possessed a meaningful distinction between forward and backward. For decades, this question seemed almost philosophical. Recently, it has become increasingly connected to active research in cosmology, quantum information, and gravitational physics. Some researchers argue that entropy explains only the direction of time, not time itself. Others explore whether time emerges from more fundamental physical processes involving information rather than existing as a basic ingredient of reality. None of these ideas has become scientific consensus, but together they reveal something important. The foundations beneath our most familiar experience remain unsettled. That uncertainty leads to a possibility that sounds almost impossible. Perhaps the universe does not merely grow older. Perhaps it gradually loses the physical conditions that make the passage of time meaningful in the first place. Notice the difference. This is not the popular image of the universe ending in a spectacular explosion, or freezing forever beneath dying stars. Those endings still assume there's a clock patiently counting every remaining second. The deeper question asks whether, after unimaginable spans of cosmic evolution, there could come a stage where change itself becomes so limited that distinguishing one moment from the next loses operational meaning. Not because someone stops the clock, because nothing remains capable of marking another tick. If every process reaches equilibrium, if every usable difference in energy disappears, if every physical system settles into nearly identical conditions, what event remains to separate one instant from another? A clock is not magic. It works only because something changes. An atom oscillates, a pendulum swings, a planet completes another orbit, a crystal vibrates. Remove change, and measurement collapses with it. That does not necessarily mean time disappears. Most physicists would reject such a direct conclusion. The distinction between time itself and the observable arrow of time remains an active subject of debate. But it does mean that our intuitive picture of time as an endlessly flowing river may depend far more on irreversible physical processes than common sense suggests. Arsiv, for almost every human who has ever lived, time has felt like the most dependable feature of existence. The evidence hints at something more fragile. Not fragile over years, not over the lifetime of civilizations. Fragile over the lifetime of the universe itself. If that suspicion is correct, then the ultimate fate of time is no longer a philosophical curiosity. It becomes one of cosmology's most unsettling unanswered questions, and answering it requires following entropy far beyond the point where stars disappear, galaxies fade, and even the familiar meaning of before and after begins to lose its certainty. The idea that time depends on change sounds almost obvious. We notice birthdays because faces age. We measure seconds because atoms oscillate. We recognize history because events leave records behind. Remove change, and the distinction between one moment and the next begins to dissolve. Yet that observation hides a deeper assumption. It assumes that change is always available. For nearly all of cosmic history, that has been true. The early universe was anything but quiet. Temperatures were unimaginably high. Matter and radiation collided continuously. Tiny quantum fluctuations were stretched across space during cosmic inflation, eventually becoming the seeds from which galaxies formed. Gravity amplified those minute differences over billions of years, pulling matter into stars, clusters, and the immense filamentary web that still defines the large-scale structure of the observable universe. Everything that followed depended on imbalance. Stars exist because gravity compresses gas until nuclear fusion begins. Planets remain warm because energy flows outward from stars. Life survives because it exploits differences in temperature, chemistry, and available energy. Even thought itself depends on imbalance. Every neuron in the human brain communicates by maintaining tiny electrical differences across cell membranes. Destroy those gradients, and consciousness disappears almost immediately. A living brain is not merely matter arranged in a particular way. It is matter continuously consuming usable energy to remain far from equilibrium. This pattern repeats at every scale. Nothing interesting happens where every difference has already been erased. Physics gives those useful differences a specific name: free energy. It is not energy by itself that allows work to occur. The universe contains enormous amounts of energy locked inside empty space, atomic nuclei, and gravitational fields. What matters is whether that energy can still flow from one state to another. A waterfall powers a mill because water occupies different heights. A battery powers a spacecraft because electrical charge is unevenly distributed. The sun shines because its interior has not yet reached equilibrium. Difference creates possibility. Equilibrium removes it. This distinction becomes increasingly important when cosmologists discuss the distant future. Popular descriptions often imagine the universe simply becoming colder. The reality is more subtle. Temperature alone is not the decisive factor. A refrigerator is colder than the room around it. Yet it functions only because electricity continuously drives heat in directions it would never move naturally. Without that external source of usable energy, both refrigerator and kitchen eventually settle toward the same temperature. Nothing dramatic happens. The process simply stops producing meaningful change. The universe appears to be moving toward a comparable destination, although on scales so immense, they almost resist comprehension. Observations indicate that cosmic expansion is accelerating, driven by what researchers currently describe as dark energy. As galaxies move farther apart, fewer remain gravitationally connected. Over immense spans of time, each surviving galaxy becomes increasingly isolated as the expansion stretches the distance between large cosmic structures faster than light, bridge the gap through ordinary travel. This does not violate relativity because space itself is expanding rather than objects moving locally through space faster than light. To observers living trillions of years from now, the universe may appear dramatically smaller than the one astronomers study today. Not because space has contracted, because nearly everything beyond their local group will have disappeared beyond the observable horizon. Information itself becomes inaccessible. That alone changes what can be measured. But the deeper transformation continues inside every remaining galaxy. Stars do not burn forever. Massive stars exhaust their nuclear fuel within millions of years. Smaller stars survive far longer. Red dwarfs, the most common stars in the universe, may continue shining for trillions of years before finally fading. Eventually, even these extraordinarily efficient stars consume the hydrogen that allows fusion to continue. After that, stellar birth slows almost to nothing. Galaxies gradually lose their brightest engines. White dwarfs cool. Neutron stars drift. Black holes continue swallowing matter when opportunities arise, but opportunities become increasingly rare. The universe does not suddenly become empty. It becomes uneventful. Imagine entering a city where every factory has closed, every vehicle has stopped, every conversation has ended, and every source of power has quietly shut down. The buildings remain, the streets remain, the physical structure still exists, activity does not. Scale that image upward until it encompasses galaxies. The result approaches what cosmologists call heat death, though the phrase can be misleading. It does not describe intense heat. It describes maximum entropy, a condition in which no significant thermodynamic gradients remain available to perform work. That distinction matters. The universe does not need to disappear for history to end. History depends on events. Events depend on irreversible change. Irreversible change depends on available free energy. As each link weakens, the next becomes increasingly difficult to sustain. This is why some physicists argue that entropy is more than an accounting tool for disorder. It governs the production of records. Every memory, every fossil, every crater on a planetary surface, every photon reaching a telescope, represents evidence that one physical state became another through irreversible processes. Without irreversibility, nothing distinguishes cause from effect. Without records, there is no operational meaning to a past. The implication reaches further than everyday intuition. Suppose an observer somehow survived into an era where virtually every thermodynamic process had reached equilibrium. Their body could not function as biology understands it. Their instruments could not record changing measurements. Their clocks could not exploit periodic motion sustained by usable energy. Even if space-time itself still possessed a time dimension, what experiment could reveal its passage? Physics depends on comparison. Comparison depends on change. And change depends on differences that the universe appears committed to erasing. The unsettling possibility is not simply that everything ends. It is that the conditions allowing anything to notice the passage of time may disappear long before the universe itself does. That raises a question more difficult than the one we began with. If the arrow of time emerges from entropy, what happens when entropy can no longer increase in any meaningful way? Does time continue in silence? Or does the distinction between one moment and the next become physically impossible to observe? At first, heat death sounds like the end of the story. Stars fade. Galaxies grow dark. Every source of usable energy is exhausted. The universe settles into equilibrium, and nothing significant happens again. But equilibrium creates a problem that reaches beyond astronomy. If nothing changes, can time still be said to pass? Many physicists would answer yes. In Einstein's general relativity, space-time exists as the stage upon which physical events unfold. The equations themselves do not require stars, observers, or even atoms to keep existing before time. Remains part of the mathematical description. Yet physics has always drawn a careful distinction between mathematical existence and physical observability. A quantity becomes meaningful because it can, at least in principle, be measured. Length requires something that can be compared. Temperature requires particles exchanging energy. Velocity requires changes in position. Time, too, has always been measured through change. Every clock humanity has ever constructed depends on repetition. Ancient civilizations watched shadows move across stone. Mechanical clocks counted swinging pendulums. Quartz watches measured vibrating crystals. Modern atomic clocks follow the extraordinarily stable oscillations of cesium atoms, defining the international second with astonishing precision. Different technology, the same principle. Each clock transforms a repeating physical process into the passage of time. Now imagine removing every repeating process, not damaging the clock, removing the reason any clock could ever function. That possibility forces an unexpected question. Perhaps clocks do not measure time. Perhaps they measure change. Those two ideas seem identical until one disappears while the other might remain. This distinction has become increasingly important in attempts to understand quantum gravity, where the familiar picture of spacetime begins to break apart. General relativity describes gravity with remarkable accuracy across planets, stars, and galaxies. Quantum mechanics explains atoms, particles, and the microscopic structure of matter with equal success. Separately, they are among the most successful scientific theories ever developed. Together, they refuse to fit cleanly. Near black holes, and during the earliest fractions of a second after the Big Bang, both theories become essential simultaneously. That is precisely where they disagree. One reason is surprisingly simple. General relativity treats time as part of the geometry of the universe. Quantum mechanics usually treats time as an external parameter against which everything else evolves. They are speaking different mathematical languages about the same reality. Attempts to reconcile them have produced an idea that would have seemed almost absurd a century ago. Time itself may not be fundamental. Instead, it could emerge from relationships between more basic physical quantities. This does not mean researchers have demonstrated that time is an illusion. They have not. It means some candidate theories suggest that what we experience as flowing time may arise from deeper structures, much as temperature emerges from the collective motion of countless molecules. A single molecule has energy and momentum, but it does not possess a temperature by itself. Temperature becomes meaningful only when many particles are considered together. Some physicists wonder whether time behaves in a comparable way, not fundamental, emergent. If that possibility is correct, then the future of time depends on the future of the physical processes that give rise to it. And those processes are changing. As entropy increases, correlations between systems weaken, usable energy becomes scarcer, opportunities for complex interactions steadily decline. The universe does not merely become quieter, it becomes simpler. That simplification has consequences for information. Every memory is a physical record. Every fossil preserves an ancient state. Every photograph stores an arrangement of atoms, reflecting a previous event. Information is never completely abstract. It always inhabits matter or energy. When a civilization builds libraries, archives, or digital storage, it is constantly fighting entropy. Left alone, paper decays. Magnetic fields drift. Electronic components fail. Even the most stable storage media eventually lose their ability to preserve distinctions. Memory requires maintenance. Maintenance requires energy. Energy requires gradients. The chain never disappears. It only extends farther backward than intuition suggests. Now imagine this process continuing not for thousands of years, but for trillions upon trillions. Eventually, every remaining record faces the same physical challenge, not because history becomes false, because the universe gradually loses the ability to preserve differences indefinitely. This introduces an unsettling possibility. Perhaps the greatest casualty of cosmic evolution is not matter, not stars, not galaxies, but memory itself. Without reliable records, causality becomes increasingly difficult to reconstruct. Without causality, the distinction between before and after loses operational meaning. Notice how far the investigation has shifted. We began with clocks. Now we are confronting information. That transition is not accidental. Modern physics increasingly treats information as one of nature's most fundamental ingredients. Black hole thermodynamics, quantum information theory, and the ongoing search for quantum gravity all point toward an unexpected conclusion. Information is not merely something intelligent beings create. It appears deeply woven into the behavior of physical law itself. If information becomes progressively harder to preserve as the universe approaches equilibrium, then our understanding of time may depend on something more fragile than motion alone. It may depend on whether reality can continue distinguishing one state from another. That possibility transforms heat death into something more profound than a cold, empty future. It becomes a gradual erosion of distinction itself. And if distinctions eventually disappear, the universe may not experience a final second. It may simply reach a condition where the concept of another second no longer corresponds to anything that can ever be observed again. For centuries, the universe looked permanent. Ancient civilizations watched familiar constellations return year after year. Even after astronomy revealed that stars are born and eventually die, the larger cosmos still appeared stable on human timescales. There was always another galaxy beyond the next telescope, another generation of stars waiting to ignite. Modern cosmology replaced that comforting picture with something far less intuitive. The universe is not simply evolving, it is becoming increasingly inaccessible. When Edwin Hubble discovered that distant galaxies are receding, the result suggested expansion. Decades later, observations of distant type Ia supernovae revealed that this expansion is accelerating. The simplest explanation consistent with current observations is a component of the universe we call dark energy. We can measure its effects with considerable precision, yet its physical nature remains uncertain. Acceleration changes more than distance. It changes the future of information. Imagine standing on a shoreline while the ocean slowly carries away thousands of ships. At first, they remain visible. Then they become faint silhouettes. Eventually, the horizon hides them completely. The ships still exist. They have not been destroyed. They have simply crossed a boundary beyond which no light can ever return. That analogy captures. The actual universe is even less forgiving. Because space itself expands, sufficiently distant galaxies can recede in such a way that light emitted after a certain point will never reach us. There is no faster spacecraft capable of closing the gap. No future technology can negotiate with the expansion of space-time itself. Entire regions of the observable universe will quietly disappear forever, not because they cease to exist, because causality no longer connects them to us. This is where the meaning of time begins to shift again. We often imagine the future as a sequence of events waiting to occur. Physics instead describes a growing separation between regions that can still influence one another and regions that never will again. Time does not merely carry information forward. It also determines what information remains physically accessible. That distinction becomes increasingly important as the universe ages. Suppose an astronomer evolves inside the local group of galaxies 100 trillion years from now. By then, nearly every galaxy outside the gravitationally bound neighborhood will have vanished beyond the cosmic horizon. The night sky would contain only a handful of merged stellar systems surrounded by darkness. No expanding universe would be visible. No cosmic microwave background would remain detectable. Its wavelength would have been stretched so dramatically that practical observation becomes effectively impossible. The evidence that led 20th century cosmologists to the Big Bang would be gone. Not hidden, erased from observation. Future scientists, using perfect reasoning and flawless instruments, might conclude that the universe is static and eternal, because every observable clue suggesting otherwise had slipped permanently beyond reach. The laws of physics would not have changed. The available evidence would. That possibility carries an uncomfortable implication. Knowledge itself has a cosmological expiration date. We usually think of scientific progress as cumulative. Each generation inherits discoveries from the previous one, gradually approaching a more complete understanding of reality. That assumption depends on records surviving. It also depends on reality, continuing to present enough evidence for those records to be verified. The accelerating universe weakens both conditions. Some truths are becoming impossible to rediscover, not because they are false, because the observations needed to reconstruct them will no longer exist inside any observable horizon. The loss is subtle. Nothing explodes. No warning appears across the sky. The archive of the universe simply shrinks. Every vanished galaxy removes another witness to cosmic history. Every stretched photon carries less usable information. Every passing trillion years narrows the evidence available to anyone still asking where the universe came from. Entropy is usually introduced through melting ice or cooling coffee. Cosmology reveals a much broader meaning. Entropy also limits memory on the largest imaginable scale. Not only biological memory, not only digital memory, observational memory. The universe itself gradually forgets its own past. That sentence deserves careful qualification. The past is not literally destroyed. The events still occurred. What changes is whether any physical process can continue preserving reliable evidence that they occurred. History without surviving evidence becomes observationally unreachable. This realization has changed how many physicists think about information. It is no longer enough to ask whether something happened. One must also ask whether the universe can continue carrying the evidence of that event into the future. Every observation is a messenger crossing time. Eventually, many messengers stop arriving. By now, the investigation has moved well beyond clocks and calendars. The real question is no longer whether time flows. The real question is whether the universe can continue distinguishing one era from another once nearly every meaningful difference has faded. There remains one place where this question becomes even more difficult: black holes. For decades, they appeared to violate one of physics' deepest principles by swallowing information that could never be recovered. Resolving that apparent contradiction has transformed black holes from exotic astronomical objects into laboratories for understanding the relationship between gravity, entropy, information, and time itself. If the universe is going to reveal whether time can survive the loss of information, it may reveal the answer at the edge of an event horizon first. Black holes were once treated as nature's ultimate vault. Anything crossing the event horizon appeared to vanish forever. Matter disappeared, light disappeared, and with them, information seemed to disappear as well. That conclusion created one of the deepest crises in modern physics. Quantum mechanics is built upon the principle that information is preserved. A quantum system may become unimaginably difficult to reconstruct, but the underlying information describing its evolution is not expected to simply cease to exist. General relativity seemed to suggest otherwise. Drop a library into a black hole, drop a civilization, drop an entire planet. From the outside, every detail appeared destined for permanent loss. For years, many physicists accepted that uncomfortable consequence because the mathematics of black holes was extraordinarily successful in every other respect. Then another discovery complicated the picture. In the 1970s, Stephen Hawking showed that black holes are not completely black. Quantum effects near the event horizon allow them to emit an extremely faint form of thermal radiation. Over periods vastly exceeding the current age of the universe, that radiation slowly carries away energy. The black hole shrinks. Eventually, if nothing feeds it, it evaporates. That result solved one mystery while creating another. If the black hole disappears, where does the information go? If Hawking radiation contains no information about everything that fell inside, then the universe appears to destroy information permanently. If it somehow does contain that information, the mechanism is extraordinarily subtle, because the radiation initially looks almost perfectly random. This became known as the black hole information paradox. Its importance extends far beyond black holes. The paradox asks whether the universe itself can erase distinctions that once existed. That question should sound familiar. Throughout this investigation, every step has pointed toward the same underlying idea. Time depends on distinguishable states. Memory depends on preserved information. History depends on recoverable records. If information can truly vanish, then the relationship between past and future becomes fundamentally unstable. During the past 3 decades, remarkable progress has reshaped this debate. Ideas emerging from quantum gravity, holography, and quantum information theory increasingly suggest that information may not be destroyed after all. Instead, it could remain encoded in ways that are extraordinarily difficult to recognize. Calculations involving the holographic principle and more recent developments using quantum extremal surfaces have provided strong evidence that black hole evaporation may ultimately preserve quantum information, although a complete theory of quantum gravity remains unfinished. Notice what has happened. The discussion has shifted away from matter. It has shifted away from energy. It now revolves around information itself. Some researchers have begun describing space-time not simply as the arena where information moves, but as something whose very structure may emerge from patterns of quantum, information, and entanglement. That remains an active area of research, rather than established fact. Yet the direction of the evidence is striking. Again and again, information refuses to become a secondary detail. It keeps returning to the foundation. If those ideas prove broadly correct, the future of time may be inseparable from the future of information. Now return to the distant universe we have been following. Stars have faded. Galaxies have emptied. Most matter has been consumed, dispersed, or transformed. Even black holes, the longest-lived large objects in the cosmos, begin their unimaginably slow evaporation. For stellar mass black holes, the timescales are already beyond ordinary comprehension. For the supermassive black holes anchoring galaxies, the process extends so far into the future that writing the number in decimal notation becomes almost meaningless. These objects outlive stars by inconceivable margins. Yet even they are not permanent. The longest-lived structures known to physics still possess an ending. When the final black holes evaporate, one chapter of cosmic history closes. What follows is more difficult to visualize, because almost nothing remains capable of complex interaction. Particles continue existing. Fields continue fluctuating. Quantum processes continue operating. But opportunities for large-scale irreversible change become extraordinarily rare. Imagine a book containing every event in the universe. Each page differs from the last because something happened. A star exploded, a planet formed, a civilization emerged, a black hole evaporated. Now imagine reaching the final pages. The words become increasingly repetitive, not because the author lost imagination. Because the universe itself has almost nothing left to write, the pages still turn. But each one resembles the previous page so closely that distinguishing them becomes progressively less meaningful. This analogy is imperfect, yet it captures the central problem. The disappearance of novelty is not merely emotional, it is thermodynamic. The disappearance of distinguishable dates gradually removes the physical basis from which clocks, memories, observers, and histories are constructed. That does not prove time ends. Physics has not reached that conclusion, but it reveals why the question refuses to disappear. Perhaps the deepest mystery is not whether time exists independently of change. Perhaps it is whether a universe that has exhausted every meaningful difference can still support anything capable of recognizing that another moment has arrived. One final possibility remains. It is the most speculative of all, and strangely, it does not ask how the universe ends. It asks whether an ending is even the correct way to think about time. There is a habit deeply rooted in human thought. We imagine endings as events, a final heartbeat, a final explosion, a final light fading into darkness. Those images belong to creatures whose lives are measured in decades. The universe is under no obligation to end that way. Its most profound transformations rarely arrive as dramatic moments. They emerge through changes so gradual that no observer could witness the entire process. The distinction between one era and the next dissolves long before anyone could point to the instant when everything became different. That perspective changes how we should think about the fate of time. Suppose the universe eventually approaches a condition where every remaining physical process is either perfectly balanced or so extraordinarily slow that no meaningful thermodynamic arrow survives. Space-time may still exist within the equations describing reality. Quantum fields may continue fluctuating. Particles may still possess measurable properties. But every familiar way of recognizing the passage of time would have vanished. No stars would rise. No chemistry would build complexity. No biological system would store memories. No civilization would compare one observation with the next. The universe would not announce that time had ended. It would simply cease producing anything capable of distinguishing one moment from another. That possibility forces us to separate two ideas that everyday language quietly merges. There is the existence of time, and there is the experience of temporal order. Physics has not demonstrated that these are the same thing. In fact, much of modern research suggests they may not be. Some approaches to quantum gravity treat time as something emerging from deeper relationships between quantum states. Other ideas preserve time as fundamental while explaining the arrow of time through special initial conditions and entropy. None has achieved universal acceptance. That uncertainty is not a weakness. It is an honest description of where the evidence currently ends. The remarkable part is that every serious attempt to answer the question arrives at the same frontier: information, entropy, distinguishable states. Whether researchers begin with black holes, cosmology, quantum mechanics, or thermodynamics, they repeatedly encounter the same realization. Our ordinary experience of time appears inseparable from the universe's ability to preserve differences. Difference allows memory. Memory allows history. History allows causality to become something more than abstract mathematics. Remove enough difference, and the concepts begin losing their operational meaning together. This is why the future described by modern cosmology is unsettling in a way that popular depictions often miss. The greatest loss is not warmth. It is not light. It is not even life. The greatest loss may be contrast itself. Contrast between before and after, between cause and consequence, between one state of the universe and the next. The irony is difficult to ignore. Humanity built clocks to master time. From sundials to atomic clocks, every improvement increased precision by finding more stable physical processes. We believe that better clocks revealed a deeper truth about reality. Perhaps they revealed something else. Perhaps every clock has always been quietly reporting the same message. Not that time exists, but that the universe is still changing. If that interpretation is correct, then every ticking clock is also measuring something far larger than seconds. It is measuring the remaining distance between the universe we inhabit today and a future where meaningful change becomes increasingly rare. That future lies so far beyond any conceivable civilization that it offers no practical warning. It offers something more enduring: perspective. Every memory you possess exists because the universe has not yet reached equilibrium. Every thought depends on gradients, established billions of years before Earth formed. Every conversation is powered by energy released processes that began inside stars, themselves made possible by an extraordinarily improbable beginning whose ultimate origins remains unknown. The arrow of time is not merely carrying us toward the future, it is carrying the universe away from the special conditions that allowed observers to exist in the first place. We often ask whether the universe will survive forever. Perhaps the more revealing question is different. If one day, nothing remains capable of telling one moment from the next, would time have disappeared? Or would the universe simply have become incapable of noticing that it was still there?